In this problem, a solid steel cylinder of 4.5 centimeter in diameter and 12 centimeter long with a mass of 1,500 grams falls into a 5 centimeter diameter vertical container filled with oil of specific gravity 0.89. Assuming that oil is incompressible, estimate the oil average velocity in the annular clearance between cylinder and container. We will find the velocity relative to the container, then relative to the cylinder. So what is happening here? You have a cylinder.
We have a cylinder on a steady flow. It's incompressible. For Q1 equal to Q2.
Okay, but look, هون Q1 equal to Q2 أو M.1 equal to M.2.
لا ما لأنه قلنا incompressible فبتصير Q1 equal to Q2.
No. بدي إياكم تنتبهوا هون you have different materials. When you have different materials, okay, so the density of oil is different than the density of cylinder. What we have here is conservation of volume and not conservation of mass. Why? Because look, what is happening is that for the same zone, if I consider this zone here, okay, for this zone, what is happening? I have the volume of this zone is not changing, but the mass inside this zone, the mass is changing. Why? Because the density of the cylinder is different than the density of the oil. Okay, but what you can say that the volumetric flow rate is the same because the volume is conserved. So the volume entering is equal to the volume that is exiting my control volume. But the mass of the control volume is not constant, it is varying. Okay? Due to the density difference between the cylinder and oil. So what I can say is that the volumetric flow rate of the cylinder is equal to the volumetric flow rate of oil. Okay? Now, for the cylinder diameter is given. So we know the diameter. So we know the cross-sectional area, which is this one. It is pi d square over 4. Okay? So Q, the volumetric flow rate of the cylinder motion, is given by this area, which is pi over 4 d square, times the velocity,
average velocity.
Yes, times the velocity of the cylinder. Now, for average velocity, we will talk for average velocity for oil, not for cylinder. The cylinder is moving at a constant velocity. It is a rigid body. Now, the average velocity is in oil because, as you know, due to no slip condition, near surfaces, you have zero velocity. Then the velocity increases in the gap. Okay? But we want to find the average velocity of oil. This is why first we should determine what is the cross-sectional area for oil. If you look for oil, you have what? You have an annular space like this, and oil, you can find oil in between here. So oil is taking place through this cross-sectional area, okay? And you know that the internal diameter is for what?
دي كبيرة minus دي صغيرة.
يعني for the cylinder, okay?
Yes, for the cylinder.
Okay, so D inner is for the cylinder, DI is for cylinder, and D outer is for the control volume.
Control volume.
Yeah, so I can say here that D from inside is equal to the cylinder diameter, which is 4.5 centimeter, okay? And the outer diameter is corresponding to the container. So D out is D of container, it's equal to 5 centimeter.
دكتور هون ليش عطونا two cases relative to the container relative to the cylinder؟
لأنه the container is fixed, okay? So when you put Q cylinder equal to Q oil, then we are talking about absolute velocities, okay? So the absolute, when we are talking about this volumetric flow rate, we are using the absolute velocities of oil and of the cylinder. Now, if you want to calculate relative to the cylinder, it will be different because the cylinder is in motion. So if you remember, I think if you have done dynamic course, you know that, for example, V relative of A with respect to B, if you have two objects A and B, V relative of A with respect to B is VA minus VB. Okay, so if B is moving and he is measuring your velocity, he will measure a different velocity than the absolute one. He will measure the difference between VA and VB. So here, since your cylinder is not fixed, your container is fixed. Because your container is fixed, then when you use the conservation of volume, you will measure the volume of the velocity of oil relative to your container, okay, which includes your control volume. So your control volume is fixed, and what is the volume going in is equal to the volume going out. Now, if you want to find the velocity of oil relative to the cylinder, you should write the following. So here, if we apply this relation, V relative
دكتور تحت هي V cylinder equal V oil.
No, it's not equal. Of course, it's not equal. Because look, to find the relation between V cylinder and V oil, you should write Q cylinder equal Q oil. Since the cross-sectional area is not the same, the velocities will not be the same. The cross-sectional area for cylinder motion is pi d square over 4, and you use the diameter of the cylinder. Okay? Now, for motion of oil, what is your cross-sectional area? You have a different cross-sectional area. So when you want to find the volumetric flow rate of oil, you will do the cross-sectional area times V oil. And what is the cross-sectional area of oil motion? It is pi d in outer square over 4 minus pi d inner square over 4. This is why here, as you can see, this is the area through which oil is moving. It's different than the area through which the cylinder is moving. So V cylinder is different than V oil. Okay, so here the result you got here is V oil absolute. So this is the absolute velocity, which is measured relative to what? Measured relative to the fixed control volume. Measured relative to the fixed control volume, which is the container. Okay, which is here, it's part of the container, Now, since they asked in the second question for the relative velocity with respect to the cylinder, you can apply this formula. If I have two objects in motion, A and B, then the relative velocity of A with respect to B is VA minus VB. So you can say that V relative of oil with respect to the cylinder is equal to V oil. Okay. Now, if you want here, you should put directions. V oil, if I take here, if I consider that this is my positive Y, positive J. Okay. So this is along J. So V oil is along plus J. Okay. Now minus V cylinder. The cylinder is moving in the negative direction. So for V cylinder, I will put minus V cylinder J because it's moving downward. Okay. So if I take J into factor, what do I get? I get that V relative is V of oil plus V cylinder along J. Okay. So of course, if a person is standing on the cylinder and measuring the velocity of the oil, you will measure a higher velocity. Why? Because the cylinder is going down while oil is going up. Okay. Any question on this problem?
دكتور
Yes.
هيدا الاكسرسايز اي بارت من
هذا
الكور
exercise, if you want this exercise is conservation, but you should understand that here it's conservation of volume, not of mass. Why? Because you have objects of different densities. So here, if you want, it's testing if you are understanding the concept. If you take a control volume, this volume inside, because you have two incompressible, you have oil is incompressible and you have that the cylinder is incompressible. So the volume inside cannot change. Okay, this volume cannot change, it is fixed. What is happening is that sometimes it contains only oil, sometimes it contains a combination of oil and the cylinder. So what is conserved in all cases is the volume. This volume is the same. But since I have objects of different densities inside this volume, so I can say that what is conserved is the volume of my system. So the volume of oil that is exiting is equal to the volume of the cylinder that is entering my system. Okay, it's not right if I put m dot cylinder equal m dot oil, because in this case I can consider that I can have if you want, since I have different densities, I cannot have the same mass at any instant. Okay, because the density of oil is different than the density of the cylinder. What is conserved here is the volume of the sport. So what you should understand is in which case I can apply continuity, conservation of mass, if I don't have mass variation in my control volume. But here I have mass variation in my control volume, because when the cylinder enters this control volume, okay, it has a different density than also, if for example, the density of the cylinder is higher than the density of oil, then the mass inside my control volume will increase when the cylinder will come in. Okay, but what will remain the same is here the volume. The volume, because my control volume has a fixed volume. Okay.
Doctor, you were saying, and I can apply continuity whenever I don't have what?
Look, continuity equation is always applied, but in continuity equation, okay, you have a transient term for mass. So here you cannot say that mass is conserved at any time. Why? Because I will show you, for example, your cylinder, okay, as your cylinder will enter the control volume. If your cylinder is now just here at this location, okay, is the mass the same inside your control volume? So consider two scenarios. This is the first
The mass
scenario.
of the cylinder, you mean?
Yeah, the mass. What is your control volume? This is your control volume, this part. Okay? This is your control volume. What is fixed is the volume. The volume of this part is not changing. Okay? Now, if I wait some time and I'll take another picture, for example, for my system, what will happen? The cylinder is going down. Then the cylinder will reach this position like this. Okay? Can you say that the mass in my control volume here is equal to the mass here?
No.
No, because you have different densities. The density of the cylinder is different than the density of oil. But what is the same for both? For both cases, for my fixed
The
control
same volume of the control volume?
Yes, exactly. So here, if you apply continuity, you should take into consideration that you have a variation in mass. Okay. So why to do the continuity if I have something much easier to use? What is easier to use here is that the volume is the same. At any time, the volume here is the same. Okay. So the volume that is entering, so the volume of cylinder, if you want, when your cylinder is going out, the volume of your cylinder that is, if you want, going through your control volume should be equal to the volume of oil that is going out of your control volume. As simple as that. Okay? And when your cylinder will leave the control volume, then also oil should enter the control volume in the same amount, in a way to conserve volume in my system. That's it. Okay? This is why here, because the mass of my control volume is changing, I will not, if I apply the continuity, I need to assess what is the transient term, what is the variation of mass. In order, because I don't want to do this, because it's complex, I will look at what is simpler. What is simpler here is that the volume is the same. Because the volume is remaining the same, so I can use the equations that the volumetric flow of the cylinder is equal to the volumetric flow of. Okay. Any other question? anyway, now once you compute the Q cylinder and Q oil, you can know how your mass is varying, okay? Because you are knowing what is the mass that is entering and what is the mass that is exiting. So here, for example, okay, in this figure, the cylinder is entering the control volume and oil is exiting. So what is m dot inlet now? M dot inlet, if you want, the mass that is entering is equal to rho cylinder, rho of a cylinder, times Q cylinder, times Q dot cylinder, okay? While the mass that is exiting is the mass of oil. So M dot of oil, which is the exiting mass, so M dot exit is equal to the mass flow rate of oil leaving the system, which is rho of oil times Q oil. Okay, so now you can compute, if you want, once you know Q of cylinder and oil, you can compute the variation of mass in your control volume. Because what is the variation of mass in your control volume? dm by dt in my control volume is equal to the difference between m dot inlet minus m dot outlet. Okay, so once you find the volumetric flow rate, you can know how the mass is varying inside your control volume. When the cylinder is entering, okay, if its density is higher than oil, then the mass inside my control volume will increase. And once my cylinder starts to exit, then the mass of my control volume will decrease. But in all cases, okay, in all cases, if my mass is increasing or my mass is decreasing, the volumetric flow rate is remaining the same. Okay.
Dr. Q is the volumetric flow rate?
Q is of, yes, QD, I mean Q dot, yes. Okay, Q is the volumetric flow rate.
Okay.
Okay. So let us continue.
دكتور بس أنا صراحة ما فهمت شو الفرق بين part A و part B.
Part A, you are measuring the velocity with respect to a fixed frame. Okay? Yani if you are standing here, if you are standing outside, your container is fixed. Okay? So if you are standing here outside and you are measuring the velocity of oil, you will measure a certain absolute velocity. If you are standing on the cylinder, you are moving with the cylinder, then you will measure another velocity for oil. It will be a higher velocity because you are moving down and oil is moving up. Okay? While if you are fixed, we will just measure V oil. That's it. This is the only difference. The difference is your position when you measure the velocity. If you are moving and measuring a velocity, it is different than if you are fixed and measuring the velocity.
هلا لأنه fixed بpart A استعملنا Q cylinder equal Q oil.
صح. بpart A it's fixed. Your control volume is fixed. صح. أنت الcontainer is moving شيء.
No.
No. So when you take your control volume, it's a fixed control volume, and since this volume is not changing, then you can write that the volumetric flow of cylinder equal to the volumetric flow of oil. Then your velocities you are including here are measured relative to the fixed frame, which is the control volume of the container. Okay. Now, once you want to measure with respect to the cylinder, then if you stand on the cylinder here, if you stand on the cylinder, you are moving with it. Because you are moving, you will measure in another velocity, which is V relative to the cylinder, not to the fixed container. Okay? And from dynamics, you have a formula. Sorry?
Just scroll down and
Yes.
see just شو عملوا بB.
Yes, I will. BB قالوا إنه V relative to cylinder is V of oil plus V of cylinder. Why they did plus? Because the formula here V oil, okay, V oil relative is equal to V oil vector, كلهم vectors, okay, V oil vector minus V cylinder as a vector. But because V oil is up and V cylinder is down, okay, so then when you apply along the upward direction, you will get V oil minus V cylinder, okay, which will give you equals to V oil plus V cylinder. And this is along positive y, okay, equal V oil plus V cylinder. And just to not confuse, these are vectors here. This V oil relative equal V oil minus V cylinder, okay? When you project on y-axis, so if you project on y, V oil is positive while V cylinder is negative because it's downward. So when you do minus minus, it becomes plus, okay? So V relative is equal to V oil plus V cylinder. This is your result. And physically, it's logic. Why? Because look, if you are standing on the cylinder and you are going down, you will see that the oil is faster, okay? Imagine that you are standing here on the cylinder and your cylinder is moving down, then for you oil is more fast than a person that is measuring in the fixed frame, okay? Any other question on this?
Doctor, but you will upload the solution, right?
Yeah, of course I will. Yes.
Okay, thank you.
Okay, another problem. Water at 20 degrees flows through a 5 centimeter diameter pipe, which has a 180 degrees vertical bend as shown in the figure. The total length of pipe between flanges 1 and 2 is 75 centimeter, when the weight flow rate is 230 Newton per second, and P1 is equal to 165 kilopascal, and P2 equals to 134 kilopascal. Neglecting pipe weight determines the total force which the flanges must withstand for this flow. Okay, so what is happening here? We have here a certain pipe system that is fixed by flanges at 1 and 2. Okay, and we have the inlet from section 1 and flow outlet at section 2, okay? And they gave us what are the pressures at section 2 and 1. So we know the pressures at P1 and P2. And everywhere else we have, when they don't mention anything, everywhere else we have the atmospherical pressure, okay? We have everywhere, we have PA. So always if you want, when you have a certain control volume and you have the atmospherical pressure everywhere, unless some locations, what you can do is you can say that if I do the summation over my control volume, okay, I can consider that PA will cancel everywhere, okay? So you have PA from all sides. This is why the atmospherical pressure overall, the control volume will cancel out. And what will remain only is what? What will remain in this case for pressures?
P1 و P2.
P1 and P2.
Yeah, but you should subtract
دكتور بس في تحت P1.
Yes,
تحت
تحت P1. We should subtract from P1 and P2 what? The atmospherical pressure. Okay? Because look, here you have already the atmospherical pressure is acting everywhere if you want. So here you have P2 from the other side, you have P atmospheric that is opposing it. So if you want, it's like this, okay? you have here the pressure. This is your pressure for this section here. For this small part here, I have P2, okay? For this small part, I know that the pressure is P2. And from directly the opposite side, which is here, directly opposite, it is PA, okay? So when I do the summation over the control volume, for this one, here I have a PA, okay? So when I do the balance, what will cancel this component is a part equal to PA, okay? So the resulting, if you want, the resulting pressure that will remain at 2 is what? Is P2 minus P2 minus PA, because this part of PA will be simplified with this one. They will cancel each other. So when I do the resultant, I will just have to include at this section P2 minus PA. And the same for this part, okay? PA at this level will cancel the pressure from the other side. So here, PA from here will cancel PA from here. So I will end up only with a pressure at this section equals to P1 minus PA. Okay?
دكتور بس ما فهمت قصة minus PA فيك تعيديها please.
Yes, I will. Okay. Look, imagine that every إذا ما قالوا لك P1 و P2 equal 165 134. إذا everywhere you have atmospheric pressure, what can you say? مش the total will cancel out. يعني if I take a control volume, if I have from this side a pressure atmospheric and from this side an atmospheric pressure, they will cancel out, yes or not?
Yes.
Okay, but now I don't have PA. I have a higher force. I have from this side, okay, from this side I have a force that is a pressure that is, it can be higher, it can be lower. It doesn't, when you do P1 minus PA, you will know if the pressure will be higher or lower, okay? So imagine that you have P2 higher than PA. What will happen? You have a certain component of P2 will cancel PA from the other side. And the remaining pressure on this part will be P2 minus PA. Because if you don't have P2, what will happen? The resultant force on your whole system will be 0, okay? But if you have P2 different than PA, you can say that since directly at the opposite side, here and here, I have here P2 and I have here PA. So if I want to find the resultant, what will be the resultant? So imagine in another way, if you want another way to explain it. Here you have P2 and here you have PA. If you want to find the resultant X force here, what will be your resultant X pressure? So here I have P2 from this side and here I have PA. What is the resultant pressure for these two?
P2 minus PA.
Yes, exactly. Because you can divide this pressure P2 into two parts, into PA and into another component which is P2 minus PA. So when you divide the pressure into two, P2 minus PA and PA, okay, when you calculate the resultant force, okay, the effect of these two will cancel out. Why? Because they are applied on. So you are taking this area and this area, same area, okay? So this the pressure component force here will cancel out the pressure component here. So you will only, it's like you only have a pressure on this side equal to P2 minus PA, okay? The same for this side here.
Okay.
No, yes.
While taking the control volume يعني فينا ناخد حتى لو بقلبها two different material بس هون عنا air وعنا water.
It doesn't matter. هلا انت your control volume فيك تاخده if you want to follow the geometry. It's not wrong. يعني مش ضروري تاخده a rectangle. But here when you consider the control volume, mainly you are considering water, يعني pipe system مع water بقلبه. This is your system. So for air you neglect, يعني air has a negligible effect. You are taking the control volume مش the air. You are considering the pipe and water inside. هلا هون you mean this here. You mean this, the air here.
Yes.
Even if, let's consider that you take this part with the system, it's not wrong. Why? Because still, when you take this part with it, you are considering the effect of the environment on it, which is also P atmospheric. So it's not wrong to take it. It will not affect your result.
So نحن بس اخذنا الكنترول فوليوم هيدا الكيرف اللي بقلبه ووتر.
فيك تاخده بس الكيرف او فيك تاخده ريكتانجل، اثنيناتهم صح.
حتى اذا اخذنا الكيرف كمان بيكون في بي اتموسفير على الطرف او لا؟
اكيد اذا اخذنا الكيرف as control volume بيصير البي اتموسفير هيك، يعني بيصير الكنترول فوليوم مثل منه uniform shape، بيصير هيك بده يلحق البايب. But as a result it's the same effect, you know, because look, pressure is everywhere. So PA is everywhere. So just at this location you have a different pressure. So also here as a resultant, and whatever is the shape of your control volume, okay? When you do summation of forces, the atmospherical pressure on this side will be cancelled out by other forces. So you will only have P2 minus PA on this side that is remaining when you do the summation. Because look, whatever is your shape, if you have a closed shape like this, you can have any form. I don't care for the form, any geometrical shape, and you have atmospherical pressure everywhere. What will happen? The total force, the total pressure force will cancel out, because if you do the summation of forces in X and summation of forces in Y, they will cancel out. So for any closed system that you have, okay, you can consider that the pressure, if it's all subjected to atmospherical pressure, in total the resulting force is 0. Okay? Do you hear me?